Excited to be here today. Thanks everybody for coming. We've got some pretty cool stuff to talk about. We've been working on it over the past 6-9 months. Really interesting things, and I hope you enjoy it. As Pratik mentioned, I'm Scott Pack. This is Nick Seo. We're on the cloud infrastructure security team at Netflix. We do pretty much the whole gamut of cloud infrastructure security at the company: account architecture, provisioning, guidance and consulting for the different application teams, platform teams, resource provisioning, vulnerability stuff, lots of fun initiatives. The crux of what we're going to be talking about today comes down to our previous inability to answer a difficult question. That question being, what AWS resources does a given application and its associated IAM role interact with? Why did we need to answer this question? In the more generic sense, we wanted to understand application behavior and the AWS resource dependencies of that application. In other words, to identify the DynamoDB tables, the queues, the topics, all the different resources that an application might rely on in order to function reliably. More specifically, some Netflix context. Some of our AWS accounts at Netflix are behemoths, highly multi-tenant, hosting thousands of different applications from hundreds of different teams, with a pretty significant base set of permissions. To better manage our IAM blast zones and address some of the single account scaling issues that we were running into, we're exploring migrating application identities out of the account where their compute and resources reside into a different account entirely. If this is interesting to you, and it should be, because it is very cool, a couple other people on our team, Joseph and Patrick, who are here today, will be talking about it in a lot more detail tomorrow. One blocker for this this application migration was to determine these resource dependencies. If we couldn't determine which resources in an account an application needed continuous access to after migration, then migrating that application before those dependencies were figured out and resource policies updated to allow continual access to them would result in a breakage. We term these resource dependencies to be account anchors. So we needed the dependency data in order to identify and then lift those account anchors. So let's talk about some of the requirements of the data that we would need to find these dependencies. First off, we needed broad service coverage. If we only had data for a single resource type or service, that wasn't going to cut it. We were using a variety of different services at Netflix. We also needed not just management events, but data events. The delineation between those two being calls that create or mutate or delete a resource versus calls that are transactionally made against those resources. An example being creating an SQS queue versus sending a message to an SQS queue. And finally, we needed resource indicators. We needed the actual resource ID, ARN, name, something that would let us uniquely identify that resource when looking at the entire Netflix environment. So let's look at some of the options that we have here. Oh, and one additional requirement that I almost failed to mention is that we needed to be able to do this without requiring application by application code modifications. There's a lot of apps. If we were to have a requirement that application owners update something in their code manually, it would have a very long adoption tail. Probably unrealistic that would be successful in any reasonable time frame. So we turned to, initially, a lot of the same data sources that every AWS customer has. CloudTrail is a good example of that. It's excellent. Everybody should have it running. Lots of good data. It has broad service coverage. Effectively, every service that's running in AWS emits those events when you create and delete those resources. However, it doesn't capture the data events that are needed to find those transactions, those interactions with DynamoDB tables, queues, et cetera. It's uncommon that an application is creating the resources. It's much more likely that it's just interacting with them after their creation. However, it does include, for the management events, the resource indicators. S3 access logs is a good exception to something like a CloudTrail extension where you can get those data events, and it does contain the resource indicators. However, it's just the one service. It solves it for the S3 visibility issue. If anyone here has enabled S3 data events at a meaningful scale, you'll know that it generates very large volumes very, very quickly. Operating at scale, you're looking at tens or even hundreds of terabytes per day, which is a lot, both in terms of complexity, storage space, and computational time and money in trying to distill all that information to something that's just that resource association that we're looking for. IAM Access Advisor is another really useful tool. Broad service coverage, effectively every API is represented in Access Advisor. It does represent both management events and data events. However, it doesn't give you those resource indicators. If your application has sent a message to an SQS queue, Access Advisor will tell you this app is using SQS, this role has made an SQS call, but it won't tell you the resource that you've actually interacted with. It doesn't let you create that resource dependency. The last one here being IAM policies really depends on how one has created those policies. At Netflix, our team is the one typically creating those. And it really depends on how, let me back up just a touch. So using those IAM policies, you can explore what resources a given IAM role has access to. If the permissions allow the application to talk to one SQS queue specifically by name, there's a pretty good indication that there's a resource dependency that exists there. There's some assumptions that your policies are crafted tightly enough with enough granularity to let you hone in on a very small set of resources. And you're also assuming that anything that it has access to, a dependency also exists. So unfortunately, none of these even combined gives us the data required to, with a high amount of confidence, associate an application directly to a resource. So after exploring those, we turn to client-side visibility. Rather than trying to pull information that AWS can provide us from the server side, from the API side, we look to what we're able to collect from the client side, from the AWS SDKs that so many of us know and love. One of the really appealing options was client-side metrics, or CSM. This is a moderately new feature, I believe, which is enabled in the SDKs by setting a AWS CSM-enabled environment variable. When that is enabled, the SDKs will send metadata about requests to a UDP listener, either locally or remote of your choice. Looked really appealing. It's easily enabled. It's natively supported by AWS. Gives options for both on-instance and off-instance collection. However, when we were examining the logs that are emitted by CSM, they're not representing the parameters used in those API calls. So kind of similar to Access Advisor, where you get the calls that were made, but you don't get the parameters to those calls. You can see an SQS send message was made, but you can't see the queue that that message was sent to. HTTP proxies are also available and accessible, and it can be enabled in the SDKs. We weren't really looking to tackle at the AWS scale volume. That would require us to intercept at a network perspective every single call that would go to AWS. Putting a bump in the line, significant scale issues. It also uses the exact same environment variable that a lot of other common HTTP libraries use to respect proxies. Were we to enable, set that environment variable and start proxying AWS API traffic, we would likely also start intercepting a lot of other API traffic and other HTTP traffic that perhaps was expecting different certificates or different network positioning than a proxy was located in. So some serious availability concerns there. The two that looked a lot more appealing were to, as a cloud security team, update the SDK. Take the SDK as available upstream, modify it with our own code, put it on our internal repositories so that as applications came up and pulled down their AWS SDK dependencies, instead of getting the upstream, they got our customized version. Downside to that was that we effectively would put the security team in the release cycle, in the release loop of the SDKs, potentially delaying teams' ability to pull versions until we get to the new version of the SDKs and put our instrumentation into those. The final one was runtime-enabled intercepts. So rather than modifying the SDK at installation time or distribution, modifying and injecting and intercepting SDK calls at the time that they were made by the app. I'm going to hand over to Nick to go into some more detail about some Netflix context and how we further explored the SDK interception options.
Excellent, thank you. Okay, so a little bit of a recap. Like, we have a gap in the data and the visibility that we need to access in order to fulfill some of our security projects. And the best path that we think is the way forward is SDK instrumentation. But anyone who's done this might know some of the headaches that come along with it. So the question is, can we do this in the same way that's going to make this all worth it and not put the security team in for a bunch of work that we don't really want to fulfill? So I'll start with a little bit of context on Netflix, mostly because there are a lot of different ways to do SDK instrumentation. And some of the decisions that we made are very specific to our environment and some of the challenges that we have. Other people doing this might have a completely different problem set, but explaining kind of where we're at will probably help shed some light on why we made the decisions that we did. So we are a Java shop. Majority of our applications are Java, over 75%. And we have a lot of paved path libraries for application development. So you don't typically start with an application that has nothing. You'll start with kind of a starter kit of an app that has, all the libraries that you need for basic interactions. And you're not doing it on sort of whatever language you want. We typically have 3-4 languages overall that would represent 90+% of the applications that we own. We also have immutable infrastructure. So typically people aren't making changes to running applications. And we have very, very frequent rebakes and redeploys. And so what this means is if you want people to pick up a library, pick up something new, typically you don't have to wait too long to do that. At most, you're probably waiting 30 days, maybe 60 days in some cases. But you're not sort of trying to interact with people to get a 3-year-old EC2 with some new code updated and onto this project that we're trying to do here. We also have a concept of consolidated logging, which will kind of come into play later. So most application logs get shipped to a central data store, and we can kind of slice and dice these in a few ways. We can do application name, we can do some metadata tags, that sort of thing. But typically, if you're just running an application, you're an application owner, you're not really worried about how your logs are getting aggregated or sent along. We take care of that for app owners, which also gives us a very nice funnel to collect some of this data, and we'll talk a lot about that in a little bit. So the first part of this is really finding kind of the right place to intercept the SDK. There are obviously a ton of options. We knew we wanted something that was in process and data rich that could fulfill some of the gaps that all of the services Scott talked about couldn't. We didn't want per client or per session code. We don't want people to make changes every time they're interacting or using an AWS SDK. And we wanted it to be very transparent to them. So they shouldn't know that their calls are getting intercepted. They shouldn't know that we're looking at them or observing them. So you really have no idea that any of this is going on. And another big one is it needs to be safe enough for production code. So if it introduces a lot of latency, that's really bad. If it breaks and they can't use AWS APIs, that's very, very bad. And so as we're kind of looking through the different solutions here, we wanted something where we could isolate failure, and if we're doing this transparently, still fulfill our needs without any application owners running to us saying, hey, you broke my application, even though I didn't make any changes. So naturally, like the first question we asked was, does AWS have something that does this? And if anyone's used X-Ray, probably they have some chimes going off in their head that, yes, this does do a similar thing. And so we started to look into X-Ray. Can this solve our problem, or at least of that problem? So eventually we found that we couldn't use it directly. So X-Ray has a very kind of trace-heavy model, and not all the applications that we wanted to monitor follow that same idea of tracing individual requests. It also doesn't support all resource types, which kind of put us right back in the case of, okay, there are some resource types we want to instrument and look at that aren't going to be visible in the telemetry coming out of X-Ray. There's also an expectation of code changes, and as Scott mentioned, we wanted to very, very heavily avoid that. So in no case did we want to reach out to 3,000, 4,000 application owners and ask them, hey, could you kind of go update this and get some of our new telemetry flowing. What it did offer, though, is some very, very interesting code paths inside of AWS SDKs that we really weren't aware of before, and some ways to instrument some of the data that we needed, get it out of the application in a way that is, for all intents and purposes, AWS approved. So at this point, we just started digging into documentation. So we started looking at the SDKs for individual languages. We started looking at the X-ray packages and libraries and how they work, and just kind of figuring out all the different nuts and bolts for each language that kind of make some of this instrumentation possible. And this ended up being a very, very fruitful endeavor because we found some primitives and some foundational work that we could build on top of and expand on top of X-ray without needing to limit ourselves to some of the same constraints as the service currently had. So we're going to dig pretty deep. I hope everyone likes screenshots of code and documentation for this. And we're going to focus on a couple of languages. For us, it's Java, but we realize not a lot of people run Java shops these days. So we'll also look into Python and go through some examples there. And hopefully between the two, we can capture most of the familiarity of what people use in their day-to-day. So this is out of the AWS SDK for Java documentation. There's a concept of a global interceptor. And this is really, really interesting because when you create a client in the Java SDK, it actually goes and looks for one of these. The TLDR is it will go try to find a file in the class path, and it will take that file and look for a fully qualified class name, and it will try to instantiate that class, and then it will feed requests into that. And there's a concept of a execution interceptor that's sitting in line between the client and the SDK and the AWS APIs. So this is really neat because rather than trying to forcefully shove your way into the path of all AWS API calls, the clients are already kind of looking for this and picking it up and then pulling it in. And so immediately this is a very, very attractive hook for what we're trying to do. There's a lot of kind of like scary words, and if you dig into it, it looks very complicated. But if you boil it down, it's actually just this. So these are the kind of the two pieces that you need, and this is a fully fledged example. You need this file on the left, execution.interceptors, that calls out a class, and then you just have to fulfill that class. There's a lot of different hooks you can then add in. For us, we wanted to do before execution, not after execution. We just figured better to pick it up as it's kind of going out the wire. And if you have these two things anywhere in the class path of a Java project, you will suddenly start seeing some requests flow through. We will not dig into all the different attributes, but if you look at that execution attributes object there, inside of there is the service detail, the API call being made, and the payload. So you have a very, very nice data structure for pulling out all the information you could ever want about the request that's kind of coming off the application. So we'll switch a little bit now. If you're more familiar with Python, it works a little bit different, but at the same time, it's really not so different. There's a concept of a history recorder. And so on the left, we have make API call, which is in line with every single API call that Bodo 3 makes. And on the right, we actually have the entire definition of what a history recorder is. So it offers a way to register a handler when the handler is enabled, and when there is an active handler, you can see on the make API call, it will record this API call object, and it will pass service and operation and parameters. So once again, this is the exact sort of payload that you would be interested in if you wanted to track every single API call being made. So again, we'll walk through a kind of bare bones example. This is actually all you need. This code will get you in line with every single API call. And then inside of emit, you can do whatever it is that you want to do, whatever you're trying to do inside of the SDK. For us, we mostly wanted observability, but sky's the limit. If you look at event type, payload, and source, again, you'll kind of get all the information that is missing from some of those other data sources. So you will know exactly what API call is being made against the service and be able to pull out whatever parameters you're kind of interested in. So that's the high level, but we'll go through intercepting an SQS send message call, which if anyone has tried to do CloudTrail or other analysis of their SQS interactions, you'll know like this is one of the many, many API calls that is typically missing. It's very difficult to figure out if you're working with an application or an instance profile that has broad SQS permissions and you want to know exactly which queues it is sending data events to. It's very tricky, but we will show that it's not so terrible in this new world. So steps on the right kind of walk through the different partitions of the request as it goes out. And we'll talk a little bit about what happens in the application code versus what happens in the instrumentation code. So start off, we talked about this before. You kind of get this global history recorder, you add yourself as a handler, and you enable it. At this point, you are sitting in line with requests. For 2, this will probably look very, very familiar. Somebody just creates a client. They don't really know that anything different is going on, but behind the scenes, when this client is used to make any API calls, we're going to start seeing some of the data flow through. So let's say they prepare an API call. And I say prepare because, again, we want to hook before any of these API calls are made. So we will actually see these events before they leave the instance and before they leave some of the client SDK code. So here's just a very basic send message. We're just adding something to a queue. And this is where our instrumentation code gets called. So if you remember before, we're going to do stuff inside of the emit function. Here, let's just print. So let's see what we're given, and let's see if it kind of matches the criteria. So if we run this, we end up getting this. And if we go look inside that payload and make it a little bit prettier, we'll see that this is actually everything that we're looking for. So this is the sort of lower level details of what's getting passed over to the API service. And this is fairly well structured for all the different services and all different API calls we'd want to make. At that point, the API call completes, and the application owner, or whatever the code is running, doesn't actually really know that their call got intercepted or observed in any way. It's just using all of the normal kind of SDK code paths they would expect. So at this point, we have like a very, very promising way to inspect the outgoing API calls. It is language specific, so we will have to have a kind of do this for every language that we want to support. But the nice thing is it's not very much code. So we were hoping to kind of get out unscathed, not own any large projects. And it's really only 100 lines or so to get this to a really, really nice place where you can start to instrument some of these calls that are leaving. It does leave you with an interesting question for deployment, which is if you now want to do this not just on one application, but across an entire organization and do it very, very transparently, how do you do that? So this inverts the problem that Scott was talking about before of like you want to own an SDK, patch it, like enforce it, make sure everyone's using it. Instead, you really just need to add a library dependency to each application. Because as you remember, the SDKs clients themselves will go looking for your instrumentation code and will kind of pull it in. And so this is a much more tenable problem to solve. Our approach was, if you remember, we have a lot of paved path libraries that we end up adding to applications. Typically, you're building on top of these Netflix foundational packages. And so if we add our libraries as the dependency of those, we suddenly have a very, very quick way to reach high coverage inside of all the applications and across our engineering organization. So in looking at this problem, it's still much, much more reasonable than maintaining and enforcing AWS SDKs. And we also don't have a lot of churn in this. So once you kind of do this, unless AWS would make any kind of fundamental change in the API code paths, you just kind of do this once and set it up. You're not really in a crazy release cycle, and your packages remain pretty standard. So if we look at a quick visualization of this, Python on the left, Java on the right, if the Python app depends on our Netflix logging SDK, which often they do because they would like logs, and those logs depend on our SDK instrumentation, suddenly we're in every single application that is using our logging platform. For Java, it's a little bit even more severe. If you would like to really do anything in Netflix, such as log, make calls to other applications, et cetera, you're probably using the Netflix version of Spring Boot. And if that depends on our SDK instrumentation, it's a very easy path into all of these different applications. So that's kind of the meat and potatoes of how we're really getting into applications and then where we're sitting. I'm going to hand it back over to Scott to talk about what happens after we capture some of these events and how we do some of the data engineering and munging to really answer some of the questions that we were originally looking for.
Thanks, Nick. So either through the Java Global Interceptor or the Bodo 3 history recorder, we end up with something that looks very similar to this. A payload object, a dictionary that informs us of the service, the operation, and all of the parameters that were used to make that API call. You can imagine this can get very large very quickly. There's a lot of fields here that we don't really need to associate to a resource. We don't need the message body, and by far that's going to be the largest. We don't need every S3 file or like object body. We don't need SNS message bodies. Those are all huge, and they don't convey any resource association information. So the first thing that we did is trim those all out. There are a couple different approaches. You could put together a list of the parameters that you're interested in across all services and capture all of those, or rather filter out anything that's not on that list. Alternatively, you can create a dictionary of services, API calls, and parameters that you're interested in, which is going to be larger, maybe a little harder to maintain, but will give you a lot better but gives us a lot better predictability about what resources, which parameters we're capturing for which API calls. It sounds like a lot of work to procure that list, and it can be. Fortunately, X-Ray has a similar pattern, and there are some configuration files that can be borrowed from that project and that we borrowed for ours. After that, we have a smaller number of very uniform messages. For the example here on the screen, we no longer have the message body. The queue URL is the same for all of these send message operations, so they're all byte for byte exactly identical. Using a TTL cache, we can capture which messages we've recorded and only emit new messages that are unique compared to the ones previously seen. This handles a lot of the volumetric problems that we could have run into otherwise. By using a TTL cache with a 24-hour expiration, we still can make sure that we get fresh data on a regular basis. We don't have to set our search periods to go back to the very beginning of the application's run, like execution, to get all of those dependencies. 1 day is typically enough. So it kind of strikes a balance between volume and data freshness. So at the end, we end up with a payload that just includes the service and operation and a list of the parameters that convey resource association info. Omitting the number of messages that, duplicate messages here, removes your ability to convey the strength of the relationship. So if you had multiple applications talking to one queue or pulling messages from one queue, you wouldn't really be able to tell who was the greater user of the queue. But that's, since we're looking for dependencies and not necessarily strength relationships, that wasn't a problem for us. When compared with the platform data sources, it checked all of our boxes. Since the SDK instrumentation is done at the client level, regardless of which service is being used, it got immediate broad service coverage. There's no distinction at the API level between management events or data events. And since we can select whichever method parameters that convey that resource association, we get those resource indicators as long as we are selecting them. One piece of information that is not included there is the caller, what application is actually making this call, which role is being used to sign these requests. A couple approaches we explored was, in our instrumentation, just use the SDK to do an STS get caller identity, and trust that whatever credential we are provided is the same credential that the application is running as. Very straightforward. The SDK is already there, so there's no additional dependencies. Really easy. However, it's possible that there could be gaps if the application is using a non-default profile or it's pulling credentials in from something other than the default credential resolution chain or priority. You may not end up with the same credentials. Other option that we explored there and ended up not pursuing was patching the SIG-v4 authenticator, the signature function. That's really the first place you see the credentials and the API call still in a dictionary format that you can get those parameters out and use the credentials to make a call-specific get caller identity call to very strongly associate those two together. It's not too bad, but since we are like Netflix, running on the Netflix paved path, that kind of non-default credential introduction is very, very uncommon and wasn't really worth the introduction of complexity. One thing we had to make sure we do is to omit STS get caller identity from our own inspection. Since the instrumentation is making that call, if the instrumentation was also catching it, it could very easily lead to accidental recursion. So we have deduplicated minified data records coming out of two different pipelines, one from Java, one from Python. One important part was to be able to abstract away the application of the SDK that was used to make the call, because we didn't want to have to keep track of that down the line. We put together a JSON message spec to make sure that our formats were identical between the different libraries that we're using, and yeah, from that point forward, it didn't matter what SDK was generating these events. They all looked the same to us. At that point, we're only limited by what we can do in code. We have the interceptor, it's minified. Where do we want to send it? What do we want to do with it? We, as Nick mentioned earlier, needed to be pretty conscious about making sure that this is lightweight. This is synchronous with the API call, meaning every millisecond that we spend handling these logs is another millisecond that the application is waiting to make that call and get it back, so it's perceived as latency. So we had to do something very fast, very local. Our approach was to add these instrumentation logs, these events, into the existing application log stream. Netflix, effectively every application running in a container or on an instance has a local logging agent, a daemon sitting right there. By taking our new events, putting an additional meta tag on it, and sending it to that daemon, the Netflix logging platform picked it up and then made it so that we can handle it remotely. That's basically the end of what we had to do locally. Very light, hand it to the daemon, get it off the box, do the rest of the processing off instance. So this resulted in our instrumentation logs being interspersed in all of the different applications log groups. So you'll see HTTP logs, application logs, and SDK instrumentation logs all in the same place. This didn't make it super nice for us from a searching perspective. If we wanted to know, get these resource dependencies across a handful of different applications, we'd end up having to query each of those applications. Fortunately, the Netflix logging platform provides a way to create a virtual log group which aggregates resources matching a certain criteria, effectively that tag that I mentioned before, into a different platform virtual application. So then we end up with just one bin with all of our logs in it from the SDKs across all of the applications, regardless of where they're running. So a quick recap on what happens on instance and what happens off instance. On instance, the SDK creates the request, sends it. The SDK triggers the intercept or the history recorder and hands that off to the instrumentation code, which does the minification, deduplication, hands it to the logging agent. At that point, it's handed off instance to the logging platform. It goes through, at that point, a messaging stream. The events at this point are still service-specific. The payloads say queue URL equals the URL of whatever the queue is, which isn't super nice to query against. So we set up a job, actually thanks to Jay Dulia here in the front. He was the one that did this work. Set up a job that consumed the events coming into that log group and transformed them into something more uniform across all services making for easier querying. So rather than QRL equals the string of the URL, key equals the QURL, value equals whatever the resource association is that we're looking for. That way we can just get a set of those value parameters, not the parameter name, just the values, and that effectively gives us the list of dependencies for the application. After doing that reformat, it submits it to a DynamoDB table via a stream. So there's a lot of like Netflix pave path hand wavingness that's going on here. The same thing could almost be set up, very similarly using AWS primitives. Rather than our logging agent, one could use CloudWatch logging agent, write those logs to a specific file or a directory on the host, send those to a dedicated logging group, use Kinesis to bring those into a Lambda function to do the reformatting, and then have that Lambda function write it to an RDS database. So very possible to do this without using the Netflix pave path. So let's go back to what the initial question was that we were trying to answer of which AWS resources does a given application interact with. Now that we have all of this data sitting in a relational database, we can just use SQL, grab the service operation key and value for a given application. And as right here, we can see the bucket names, slightly sanitized, the queue names, again, slightly sanitized. If there were any other resources that this application was talking to, we would see them right here. There wasn't any service-specific or service-specific customization, no application modifications, just a rebuild and a redeploy of this application, which at Netflix happens for every application on a very high frequency. So I'm going to pass off to Nick to go over some of the next steps some of the things that this is unlocking for our team and some of what we look to do with it going forward.
Thank you. Probably the first thing to start with is it works, which is really, really nice. So we are seeing about megabytes a day scale, and it is fairly real time, and we are able to answer questions that we really haven't been able to answer before, and probably most AWS customers can't answer. So if your application is interacting with certain resource types, you can probably answer it, but I'm sure anyone here who's like gone through CloudTrail has given the answer, like, we just don't know, we can't really answer that. And so we were trying to say that a lot less, and we have been successful in doing so. Some lessons learned. On the technical side, there's a lot of parameter name overlap between services. A KMS key is very different than an S3 key. And when we are parsing all of these requests and we are kind of treating every API call exactly the same, there's quite a bit of cleanup that we have to do in order to understand exactly what we're seeing and the exact resources that something is interacting with. We have a fairly small number of very high resource touch applications, which are to say, like, they actually break the logging in the sense that they just interact with everything all over the place. It's not super useful to know that something that touches every IAM role is touching every IAM role. It's not useful to know that something that interacts with every EC2 is doing with every EC2. And so we've added some exclusions on our logging side to kind of cancel out the data that just isn't terribly useful for us. As we were going through all of the different SDKs, we learned that they have very different views of AWS. So the way that calls to AWS get created, the way that we intercept those, the way that we access the data, the life cycle of an AWS request is very, very different. So we did have to kind of learn, like, what does Java consider an AWS request to be versus Python versus Go versus JavaScript, that sort of thing. It was a very interesting and enlightening piece of learning, but overall we found that we could treat all of these different languages and all these different clients about the same. There's just a little bit of a technical asterisk on how you go about getting the data and handling some of the requests. On the strategic side, we found that it was very useful to piggyback on carrots. So we talked a lot about how we get these libraries into applications. I do not think that this would have been possible or really fruitful if we had to go around forcing people to do things, if we had to convince them that they need to get their applications instrumented. That's a very different value proposition than like, hey, you just want to do normal stuff in the platform with your application. we're also there kind of collecting data as you do that. So from a adoption and migration perspective, like the only reason we were able to see the numbers that we did was because we found an approach that let us align with what people already wanted, which is very, very useful. As far as what's next, what's possible, I'm sure anyone here who's looking at this and saying, oh, I have whatever code I want in line with any AWS request that's going out is like the gears are turning. There's a lot of possibilities. Same for us. So the first one is one that we mentioned earlier, taking this usage data, rewriting resource policies, and really understanding what needs to change when you take an application identity, move it around between different AWS accounts. That was kind of what caused us to start researching this in the first place, and one of the primary usages of the data. We also realized during this that you can inspect the responses just as easily as the requests. And so this gives us a very nice handle for doing some real-time permissions troubleshooting and debugging. When you see an error come back, the error code is access denied, you know in real time that an application is failing to access something. And specifically on API calls that you wouldn't know from CloudTrail. So again, if you've ever tried to craft a policy off of CloudTrail, it's probably missing a good bit if you're depending on the resource types you're interacting with. And this gives us a nice way to sort of complete the rest of that coverage. The final piece is really understanding the full scope of operational dependencies of apps. This is something that has been difficult to understand before, as far as, if we were to do something to an S3 bucket or a queue or a topic, who might break, who might be affected, who's downstream of this. Sometimes application owners know, sometimes understandably they don't. And so this gives us more of a data-driven approach to figure out some of those dependencies and expose back to application owners, like you might not even know this, you might just be importing a library, doing something you're kind of unaware of, but you are dependent on these resources in the same AWS account, the other AWS accounts, et cetera. So it's definitely like an unexplored area for us as far as digging further, but we would like to take some of this data that we have now that we're summarizing kind of the full list of resource dependencies and see what we can do with that, who would be interested in it, and what views would help increase developer productivity and robustness of apps. So with that, that is the end of our presentation, and we are happy to take any questions or ideas, feedback, etc.